So our next speaker is one of the co-organizers, and I only mention that because he's put so much effort into this. And there's a lot to say about Pete, but he gave basically a one-liner, is the technical lead of TensorFlow Mobile and embedded team at Google, and previously CTO of Jetpack, which was acquired by Google in 2014. And I think it's just short because he'd rather be demoing TensorFlow-lite than having me talk about it. So I'll let him get to that.
Awesome. Thanks so much, Kurt. And yeah, thank you so much, everyone, for being here. It's really so cool to see like this full room. When me and Evgeny were first talking about this back in August, we were really trying to figure out, how many people are actually going to be interested in this stuff. We were super excited about it, but it felt like this very weird intersection of, these very specialized fields. But the response has been amazing. And watching through all of these talks, I've learned a whole bunch of stuff that I never knew. So I'm really excited to see this all coming together. So yeah, I'm an engineer on the TensorFlow team, specifically focused on TensorFlow-lite for microcontrollers, which is kind of a brand new thing. We've really been working on it through 2018 to get the stuff working on these tiny computers. And really my goal here for this talk is to get your help. This is an open source project. What I want you to take away from this, everything I'm talking about here, is that this really is a community-driven project. Even before we announced, we actually had a bunch of check-ins from a bunch of the companies here into the code base to help support their chips. And I'm going to be coming back to that theme again and again. Like, we can bring some stuff to the table. We have some, access to a bunch of really smart machine learning people, and we can do benchmarks and things like that. But we are kind of figuring out our way through the hardware space, especially, and really, really want help from the hardware companies and the people with applications. Like, one of the best questions I heard earlier was, what is going to be the killer app? Like, we don't know. Like, we're pretty convinced that there's going to be one, but it still feels kind of like, personal computers back in like the early 80s, where people were just filling out address books on their personal computers and then like kind of going to them to look up people's addresses, when you would have just been better off looking something up in a, a Filofax or whatever it was in that day. So one of the things I want to do actually is call out the other TensorFlow team members who are here. If I can just start off with Kanksha. And I'm calling them out so that you can corner them and actually ask them about some of the stuff they've been working on. There's Rocky over in the back there, who's a lot of anybody who's dealt with the hardware side of TensorFlow-lite will have been talking to Rocky a lot as he actually gets the boards up and running. He has a magic touch. Is Raziel in the? So Raziel, stand up, because he is the master of quantization. We actually have a team devoted to trying to improve our quantization support in TensorFlow, especially on the training side. Just because we see it as being such a high value thing that we actually want to work on. And we also feel like it's something where we're in kind of a really good position to help, especially with the training side, in a way that a lot of people would like to have quantized networks coming out of the end, but it can often be very intimidating to try and figure out all of the ML side and the systems engineering side of actually getting that into something like TensorFlow. So we're putting a bunch of resources into trying to make that happen. If I can just point out Tim too, our product manager. So he is on the prowl for use cases. We love highlighting case studies of people doing really interesting stuff. We love having people up on stage talking about really cool projects. And I'll also point out Dan, who's actually put together the code lab and is doing a bunch of the documentation. And I knew we needed Dan on our team after I chatted to him during the interview, and he told me about working in an insect farm in the East Bay. That's right, isn't it? Actually using embedded machines with in this warehouse where they were growing crickets for human food. Anyway, sorry. Might be too much information, but like having to deal with actual sort of bugs in your hardware was pretty impressive background. Okay, so what is it that we're building? I'm not going to spend too much time on this, but TensorFlow Lite is the part of the main TensorFlow project, and it's aimed originally at especially mobile use cases. So when you need to build machine learning into apps within Google internally, we use TensorFlow Lite across things like the Assistant and a whole bunch of other apps. Anywhere where we're doing kind of on-device machine learning, TensorFlow Lite is the framework we use internally. It's also used externally by lots of apps out there. And it's small. It's like a few hundred kilobytes, but it's not small enough for microcontroller use cases, or it wasn't. So what we have done is basically put TensorFlow Lite on a severe diet and made it small enough and easy enough to port to run across a whole bunch of the wild and wonderful embedded processors that are out there. So I'm going to take my life in my hands, like I did at the TensorFlow Dev Summit a couple of weeks ago, and see if I can give a demo. Now, the nice thing is none of you can see these LEDs. So you'll have to take my word on this. But what this is it's actually a board that you can buy from SparkFun. That's $15 retail. It has an Ambic Apollo 3 Cortex M4 CPU on it. And it also comes with a couple of microphones and an accelerometer built in. And what I'm going to do now is just yell, yes, yes. Believe it or not, the yellow light lit up. When I said yes, there's video proof at the TensorFlow Dev Summit that if I shouted at it long enough, it would actually light up. It's definitely not up to Chris Rowan's sort of noise standard, but you could actually buy this board. You can download the code. You can follow the tutorial that Dan put together to do everything from grabbing the data, training the model in TensorFlow, and then downloading it onto the device together with the example application. And this is all available for you to play with yourself. So what are we trying to do with this? So when we looked at what you needed to do to be able to run on these microcontrollers, it was actually kind of shocking for me. Like I didn't realize, until a couple of years ago, how constrained these microcontrollers were, and that every sort of single kilobyte matters. So we knew we needed a framework that wasn't just a few hundred kilobytes of code size, but was down in the sort of, very low sort of 5, 10, 15 kilobytes of code. And we needed models that were in that same sort of range too. Luckily, Raziel actually has done a lot of work on the speech team over the years, and he was the first one who introduced me to very, along the same veins of the Siri talk earlier, the pioneering work that the speech community has been doing in these very small models, and the fact that you're actually able to do really useful things with these neural networks in just like 10 or 20 kilobytes. So the other thing that we worked really hard to do was make sure that we were part of the main TensorFlow ecosystem. because we were just talking about things like quantization. I've done a bunch of kind of custom inference backends over the years, and they're really fun to get started with. Getting something up and running and being able to show off, do sort of some models is actually, it's pretty cool, and it's a really good way to sort of, figure a lot of this stuff out and like learn about the networks. But the maintenance of actually having to write translators from, whatever the crazy researchers are doing now, every time they come up with a new op, every time they do sort of a new network architecture that changes like the optimization assumptions and things like that, it gets really, really old. And it's very, very hard to scale up that kind of work. So we've tried very hard, even though we're very, very slimmed down, to stick with the file format and the APIs, and so inherit all of the documentation and the tooling and a lot of the sort of models and things like that that come as part of this big, rich world that the TensorFlow contributors have actually been able to put together. Now, the other requirement that kind of pulls in the opposite direction of that is we know that people, especially in the embedded world, need to do a lot of specializations. They need to do a lot of optimizations. They need to do things specially for their kind of weird, funky hardware that they have. So you have to be able to hack this. Like, this is not going to work if people kind of have to download like a 10,000 file repository and then like wade through all of this stuff if they're just going to be able to sort of optimize like a convolution operation for a particular model, or just get something up and running. So we've tried as hard as we can to make it embedded developer friendly in terms of you could actually just download a very, very small subset of a few dozen files and build a working example like the speech example using that. We are working very closely with Embed and Kyle and a lot of the industry standard IDEs. Like, we want to come to where developers are. We don't want to force people who are doing all of this Windows work to have to figure out like, GCC and make files and, bash and all of this sort of stuff. And our prime goal is to really give people a good set of specifications in terms of reference code and unit tests and example models and example applications and benchmarks, kind of injecting what we found and what we want out of the other end of these these hardware systems in these very concrete technical terms, and then see if we can actually get the help of the embedded developer community and the hardware vendors to optimize and take those specifications and figure out how to satisfy them by writing really, really optimized low-level code, by coming up with hardware blocks and hardware strategies that kind of meet these requirements as they're expressed in real applications. And that's why I'm saying we really, really need you. I'm hoping that over the next sort of, over the next few months, over the next few years, I actually get to spend a lot of my time working on pull requests that are coming in from outside. It's already, like I said, it's been really heartening to see a bunch of hardware vendors jumping in already and coming up with some really high quality contributions. And I'm really hoping that that continues. And we see our role as really trying to communicate what we know about ML requirements and trying to open up the door to lots and lots of really interesting approaches to kind of meeting those requirements within this kind of like common framework of like this standard set of ops, this standard set of unit tests and models and things like that. So, you know, that's pretty easy to say. It's like a very, in a lot of ways, very contradictory set of requirements that I've laid out there, that it has to be kind of standard and conforming with this big world of TensorFlow, but it also has to be easy for embedded developers to kind of pick up and start hacking on. So what I was going to do was, you know, I'm not going to expect you to sort of, you know, absorb all of this code that I'm throwing at you right now, but just to get you thinking, I'm going to show you what it looks like and what I actually ended up doing sort of late at night, shortly before I had to finalize the software that I was going to flash onto this before the Dev Summit in order to actually speed up a model that I actually cared about. And the problem I had was that we have a convolutional model that's taking spectrograms on this chip. And we take the last second of audio, run the convolutional model to do a spectrogram sort of match every, you know, however often the inference can run. And it was only running at maybe like 4 frames per second. And that really hurt the accuracy, because the way this works is it's able to sort of do post-processing to sort of average the results that it's getting, and it gets a lot more accurate if you can sample a lot more frequently. So in order to have a demo that would actually work, I really needed to speed things up. But luckily, most of the time was going into the depth-wise conv implementation. And what we do is in TensorFlow Lite, for microcontrollers, we give you what's essentially a very cut down reference implementation. And the essential inner loop of the implementation for depth-wise conv kind of fits in one slide. Like I said, I'm not expecting you to absorb this, but the key thing here is that it's doing a whole bunch of redundant calculations in order to be more readable. So we don't expect the things that we ship out of the box to be particularly fast, but what we hope is that these reference implementations plus the unit tests that you have to sort of pass if you're going to be writing a compatible version of this will help people write their own optimized versions by looking at my terrible code basically and saying, oh, I can do way better than that, and going ahead and building it and making sure that it passes the tests and that things like running models through it actually work. So what I actually ended up doing was taking that original implementation, figuring out that I could do some magic if I actually altered the weight format layout so that I had sort of, you know, the channels as the last sort of incrementing value rather than, you know, being third in the thing. And, you know, basically was able to do a bunch of weight reshuffling beforehand at initialization time. And then I also noticed that the filter, the depth-wise conv layer that was taking most of the time actually had a filter width of 8. Which was quite nice because that meant that I could load it as 32-bit words. These were actually, let's see if, so yeah, here's where I'm actually doing the weight reshaping. But the key thing I did, which will look familiar to anyone who's done any of this kind of loop unrolling for optimization in any kind of embedded code, was say, oh, instead of loading like 4 bytes individually, I'm going to load all 4 bytes as a 32-bit word and then kind of extract out the bits I need, and then do that a couple of times. And that actually got me up to sort of 15 frames per second, which was enough. If I yelled at this enough, it actually gave me the result I was expecting. So the nice thing about that was it actually, it actually was pretty straightforward to do. And I'm planning on writing a tutorial going through this stuff. And that's really what I'm hoping people will actually be doing themselves out here for different, I'm hoping that the path of least resistance will be people starting with a bunch of standard reference ops and existing models and unit tests and kind of hacking on them from there. Even if you don't submit it back to the open source version, we're quite happy to support people who want to do their own sort of custom forks. And they're still staying within the TensorFlow ecosystem. So that is really my message that I want to get across is start hacking. We're very happy to help you. Come and find us, tell your friends. And talking of which, I'm going to ask Akanksha, my colleague up here, to talk about another way of contributing that we're hoping will help a lot.
Hi, everyone. Thank you, Pete, for inviting me. So after audio, of course, the next target was vision. We have been talking about vision use cases a lot. And I think this audience doesn't need convincing, but one of the most popular use cases that has come up is to see if there is a person in that image or not. So we started with that presence classification use case and want to extend it to object counting or localization. But what we found was that, okay, we want to train a model. Where should we start? And ImageNet is classifying to 1,000 classes, so the model ends up being too big. We saw a whole bunch of results on CFAR10, but those are 32 by 32 images. So is my model accuracy actually going to scale? So we needed an ImageNet for microcontrollers. And we will be releasing this data set in early April, which is derived from COCO data set. And it has about 150,000 images that are labeled and that two labels, person, not person, as long as the person is bigger than 5% of the image area. And what we look forward from you guys, and it would be really nice, is that we want models that fit between 250 kilobytes of RAM and a similar flash size. And we have benchmarked on our side and seen that we can compress mobile net architectures to that size with 90% accuracy, but I'm sure you guys can do much better and much faster. And I look forward to interacting with you in the poster session. So I would love to get more people interested and interacting with us in this model design problem and deploying it on hardware. Thank you.
Awesome. Thanks, Akanksha. So one last thing I meant to say as well. I know I'm all that's standing between you and mingling. So I'll try and keep the QA fairly short. But my email is petewarden@google.com. That's my name at google.com. If you have any questions that aren't answered in this Q&A session, or if you want to follow up about any of this stuff, please do drop me an email. I'd love to hear from you.
Okay, we do have a question here.
Yeah, you're putting a lot of focus, obviously, in the libraries and optimizing it, but there's a lot of work going on in these compilers. Microsoft just talked about when there's Glow, there's the Amazon one. Are you guys looking at all that? Because that's obviously, there's a lot of optimization options. You do graph lowering, fusing, looking at opportunities that relate to the hardware that's harder to extract out of a loop. Because compilers aren't that smart, right? I mean, the normal compiler doesn't see it. But that's the point. Are you looking at that as well? Because that's going to have a huge play in this kind of more deeply embedded space.
Oh, yeah. And what we really see as the biggest value that we bring is actually the tests. And the practical use cases. Like, we're actually fairly agnostic about what's happening to run these networks. But the only way that we're going to make progress as a community, we think, is if we actually have a rich set of example models and example applications and like unit tests and model level tests and like reference code for.
But with tests that, with tests that adapt to things like compression, quantization, pruning. Because I mean, that's one of the problems. As soon as you apply all that, most of those tests fail, right? Because you get slight variation in results and you're looking for fairly precise results. And you know, those are trade-offs, and sometimes the average is pretty good, but you know what I'm saying.
Well, and that's really where we see the model level results as the gold standard. And like you say, it gets harder once you move away from individual unit tests. But with this, like visual wake word is a great example. We're going to be sort of publishing, we're hoping to publish our own examples of like, here's evaluating this on like an actual device, rather than just evaluating it in an emulation that's running in Python. Because yeah, we have exactly the same problem where you don't care about like the least significant bit changing on these things, but what you really care about is being able to run this across a representative data set using whatever hardware you actually are going to be running on. Because at the moment it's kind of the Wild West and it's very hard. So I mean, yeah, I agree. I think testing is really hard, and that's why we see that we have to do that anyway. And so we want to try and open it up to as many people as possible and get collaboration on that. Because yeah, I think you've hit it on the head. It's like really hard to do that stuff.
So while the audience is building up their courage, I'd like to kind of follow up on a related question.
Yeah.
So quantization and other aspects of neural architecture search are becoming amenable to incorporated in the training optimization framework. I think Google has 3 different projects: MNestNet, AutoML, and what am I forgetting? NetAdapt. Right?
Yes.
So or NetApp.
Something.
One of those. Vivian Say's work when she was visiting there. Are any of these being incorporated? Can you name names here a little bit?
No, I mean, definitely. Like, I think Raziel is actually a really good person to talk to about, especially the quantization side of this stuff. And, you know, Andrew Howard on the MobileNet side is working very closely with the MNASNet team. Right. And one of the things we're doing with a lot of the architecture search, because like the first generation, they just looked at multiply ads. And then when you came to run the model in TensorFlow, it turned out that it was, even though these things, some of them had lower multiply ads, they were actually slower than other architectures. So we've actually been doing a lot more work running this stuff on farms of real devices, and actually trying to, it's one of our goals as well, is, if we're able to get a fast iteration loop between creating a model through genetic algorithms or something on the training side, and then very quickly running it on a real device to see what the performance is like, rather than just guessing,
right,
then we should be in a much better position to find these things.
Yeah, I see where you're going there. I mean, but the analog going, since I think we have a lot of circuit types here, one analog back in the day was you could target a circuit to every single library, or another possibility was to build a general model of libraries and then be able to better estimate the circuit. So are you doing anything a level higher than what you described of using than just building farms of an experimentation, but actually trying to build a more general model? Because it seems like microcontroller, no jab at ARM or something, shouldn't be that hard to model, right? Right.
Well, I mean, I think I come back to Jeff's slide where he talked about like the 26,000 times, increase with all of these different techniques. Like one of the hardest problems we find is just keeping up with all of the shifting, architectures and things that are happening there.
And there you mean network, deep neural net architecture.
Deep neural network and hardware.
The target hardware.
And hardware, like everything's changing at once. And that's partly why, just to kind of preserve a little bit of sanity, we have such an emphasis on testing and trying to come up with benchmarks and actually tested suites and things, because otherwise it's hard to tell even if something's better or not.
Great. Okay, well, I didn't mean to.
Sorry.
Do we no other brave souls?
Cool.
So, then we'll keep talking.
No, I can escape.
Okay. All right. Thank you.
There we are.